Hey, we're looking at class 92. So first thing we did was we looked at the simulation with electric fields. We found that electric fields always point away from positive charges and toward negative charges. Then we put one positive charge on top of one negative, which effectively creates no charge, right? Because one positive, one negative directly on top of each other has no charge total. And we saw that the electric field disappeared because you need a charge to have an electric field. We found that the closer you were to a charged object, the stronger the electric field. The farther you were from the charged object, the weaker the electric field. So then we started measuring electric fields. So your data might be a little bit different in class, but you should see the same relationships. So when we put a electric field sensor 5 boxes away from the charge, we saw that the electric field was 1.46 volts per meter. Then we moved it to 10 boxes away. We saw that the electric field strength dropped to 0.36 volts per meter. We expected it to go down. What we noticed was that when we went twice as far, we didn't get half as strong. We got 1/4 as strong. Okay, so when you go twice as far away, you quarter the electric field strength. Okay, and going the other way, if you cut the distance in half, you quadruple the electric field strength. This is that classic inverse square relationship that we've seen before. Notice here, this is a graph of electric field strength versus distance from the object. That's an inverse square relationship graph there. Now we left the sensor at 10 boxes away, and we added a second positive charge right on top of the first one, effectively doubling the charge. We saw that the electric field strength became 0.72 volts per meter. So we found that if you double the charge on the object, you double the electric field strength created by that object. Going the other way, if you cut the charge in half, you cut the field strength in half. This is a linear relationship, which we drew over here. Electric field strength versus charge is a linear relationship. As one goes up, the other goes up, exactly the same. So here we just drew electric fields around charged objects. We have electric field going away from a positive charge and toward a negative. We said that electric field lines can never cross. So if we're drawing interacting field lines, they kind of have to either connect or avoid each other. All right. Notice how positive to negative, they leave a positive, go into the negative, positive, positive. Notice how they point away from the positives and they kind of curve upward. They don't cross each other. And negative, negative, see how they kind of curve into each other, again, not crossing. And also it's important to note, we said this already, that electric fields are weaker as you get farther away. Now electric field between two charged plates goes away from positive and into negative, away from positive into negative. Okay, and it actually goes down perfectly straight lines. An important feature here is that between two charged plates, the electric field strength is the same everywhere. The electric field is equal at A, it's equal at B, it's equal at C. Therefore, the forces that charged objects will feel at A, B, and C are also equal. Okay, very important point. By the way, these are two charged plates, so you could picture like this is like a sandwich, and these are two pieces of bread. These are three-dimensional. This positive thing is a charged flat plate that goes into the page. Same with the negative. Now, even though the electric field is equal everywhere between the two plates, if the plates were put farther apart, you can kind of tell how the electric field would get weaker in that case. So some of the electric field line rules. They always point away from positive and toward negative. They never cross. This next one we haven't really spoken about yet. Electric field lines always intersect the surface at right angles. Look at this picture to the right. Notice how the electric field line here, the correct one, points away from the positive charge at a right angle to the surface. The one with the X through it, that is not at a right angle to the surface. Electric field lines, stronger electric field lines mean they're closer together. The weaker electric field lines will be farther apart. Electric field strength and line density decrease as you move farther away from the object. So here's a positive charge with a strong field. Here's a negative charge with a weak field. More lines equals stronger, fewer lines equals weaker. Here we had to predict what the charges were on A and B. We predicted that they were both negative because they both point toward, all right? If these arrows were pointing away, they would both be positive. So what's the deal with electric field lines? Why do we use them? What are they? Well, the electric field depicts the direction that a positive object would move in that field, okay? So to an extent, if you put a positive charge in this field up here between these or around these two negative charges, it would roughly follow the path of one of the lines, okay, kind of. Then we went through these and we discussed which electric field arrangements are or are not possible. The only one that is possible is number 1, because the electric field lines point away from positive and into negative. All the other ones point away from negative and into positive. Those are wrong. So positive charge, just kind of adding on, would go with the electric field lines. It would go down. Negative charge would go opposite the electric field lines. Right, and there's our introduction to electric field lines and how to draw them.